So, good morning, good afternoon, good evening, depending on your time zone. Welcome to day 3 of this Arctic Colors Coastal Arctic Biogeochemical Data Synthesis Committee meeting. We'd like to thank the Ocean Carbon Biogeochemistry Program Office, especially Heather and May for helping us coordinate and organize this virtual meeting, as well as supporting this data synthesis activity. And also NASA Ocean Biology and Biochemistry Program, Laura Lorenzoni, program scientist for supporting this data synthesis activity as well. Okay. There we go. So yeah, hopefully you may have joined us on day 1 and day 2, where we talked about focused our discussions on field measurements, what data sets exist in the coastal Arctic. Day 2 focused on modeling activities. And day 3, we're focusing on remote sensing, though I don't expect us to go in depth on remote sensing specific issues. It's mostly we intend to address remote sensing in relation to this field measurement data synthesis activity. So this is I'll go through this again later, but just to point out that I'm going to try to give you an introduction, provide some context to the Arctic Colors timeline going forward, as well as for this data synthesis activity. And then we have a series of speakers, exciting topics today, and I'll go into a little more detail later. Okay, so Arctic Colors, what comes next? I know that that's come up during this meeting and you know, in other venues when people we've been able to gather and discuss. But just to be clear, Arctic Colors is the next NASA Ocean Biology and Biogeochemistry Program major field campaign. Currently, NASA OBB is supporting the exports field campaign that you may have heard about, oceanographic field campaign looking at carbon fluxes and in topics such as the biological pump in major ocean basins. They just completed their second field cruise this past spring, and so they are working on their data analysis, and will be and then the exports team will be proceeding to a data synthesis activity or a data model remote sensing synthesis activity in the coming years to come. So when that concludes, Arctic Colors is next in line in the NASA OBB planning for a large field campaign. Just to remind you all that our goal is to improve our understanding of and prediction of rapidly changing coastal Arctic. You've seen this graphic earlier this week. It's obviously in the science plan as well, but our aim is to integrate field observations, modeling, and remote sensing. Truly integrate. I think because the fact that this is largely coastal, we have access to airborne remote sensing. We obviously have satellites because they're in orbit, and also an extensive amount of field activities encompassing small boats, larger vessels, potentially larger vessels, as well as autonomous systems, gliders, moorings, various other autonomous systems. Just to point out that the science plan is available online. It was completed in 2018. It details the science questions and the knowledge gaps that were known at the time and when it was completed. It addresses how we would, it describes how we could address the science questions that were posed, involving obviously field observations, integrating those with models, bringing in remote sensing as well for the spatial and temporal context that's not possible with field observations. But also there's areas that remote sensing cannot help us, for example, seeing under ice plumes. So the field measurements are critical, and obviously the models, you know, fill in additional gaps both in terms of hindcasting and in forecasting, as well as time and space, the four-dimensional time and space. Okay, so just to give you a notional timeline, Remind you of our study region being this pink shaded region along the coast here, Beaufort, Chukchi, and Bering. Generally from the lower portions of the rivers, river mouths, and both large and small rivers, and extending into the lagoons, the erosional bluffs, and out into the continental shelf waters of these seas. Okay, so right now we are in the pre-Arctic colors phase. We're conducting a data synthesis activity. The objectives are to identify data sets from past and present programs that are relevant to Arctic colors. This particular activity that we're focusing on today advances this task, but it will go beyond the duration of this OCB, OBB supported synthesis activity. We expect NASA to establish an implementation team to develop an implementation plan for Arctic colors. We expect this to include participants, scientific members from the U.S. And very likely Canadian, international, and other international partners. We do expect that we will be engaging members of the local communities within the Canadian and U.S. Coastal regions to be part of this implementation team for advising and providing local knowledge. In the next in a few years from now, we expect NASA to solicit for actual research studies for fieldwork, modeling, and remote sensing. And we also hope that there will be willing partners that will solicit complementary investigations, potentially NSF, BOEM, NOAA, among other entities, as well as Canadian and other potential international partners. Just to point out regarding the partners outside of NASA, this will be something that the NASA program manager like Laura Lorenzoni would be heading up. It wouldn't be something that I or any of the co-leads on this activity would be engaging in, because it's beyond our purview. The actual field campaign modeling remote sensing activities would begin hopefully in the 2025 timeframe. Again, this is notional. And then that after that period of field modeling and remote sensing, we expect there to be a data synthesis activity. So this is a very long-term activity. You know, if we start the clock about now, it's basically a 12-year activity overall, with formal funding in terms of the program to be roughly on the order of 8 years. That's what we recommended to NASA. You saw a version of this slide with Ann Kellerman's presentation on Monday. This is just a little bit more comprehensive to put things into context. So we're basically here now with this OCB, OBB data synthesis activity. Again, an implementation team should be established within the coming 6 to 12 months to develop that. But in that interim, we expect there to be additional this phase 1 Arctic colors activity, which is to expand data repositories, remote sensing data sets, and also modeling development analysis. I would want to point out that NASA has been supporting a number of projects that fall under pre-Arctic colors, under pre-Arctic colors, and then just the schedule, the notional schedule for field work and other research activities. Okay. So meeting goals, as we've discussed in the previous 2 days, identify and characterize existing field data sets, modeling activities, and remote sensing capabilities within the coastal Arctic region. The emphasis of this particular data synthesis activity is on carbon stocks and fluxes, along with optical proxies, but also we are interested in related biogeochemical variables such as nutrients and primary production. We would very much like to, data sets to be contributed by November 30th. Let me skip over this for now. I think there we go. So the notional timeline of the activities, for the data synthesis that we're discussing today. To review and format contribute data sets from now. Actually, this began in the summer time frame in terms of mining of available data sets. And continue probably for the next few months. Organizing data files to consisting formats and units, quality control. These data files will be archived into this NASA system called ADAPT. This is similar to what Above is using, and Peter Griffith, I believe, will talk about that later today, about the system that Above has been using. The intent is that, well, the databases or data archive that is being created from this activity will be public. Anyone should have access to it. So that's an important aspect. We also expect that there will be some GIS capability for searching and for visualizing the locations of these data sets to facilitate access. And there'll also be a synthesis of the data sets, including data analysis and visualization, and a manuscript, or perhaps one or more manuscripts to come out of this activity. And that will be spring to summer for that activity. Okay. And so for further information, please reach out to any of us. Also very important for Arctic Colors. Obviously, the funding has not been identified because this is several years out into the future, but it would help Laura Lorenzoni immensely if you reach out to her and express interest in Arctic Colors. This is how she can gauge the interest in this and share that with her managers, including Jack Kay, who's her immediate supervisor, as head of the research and analysis and Earth Science division at NASA headquarters. So reaching out to Laura specifically, but also feel free to reach out to Jack Kay if that also would be helpful. And so our schedule today, we've got Hajo Eicken from University of Alaska Fairbanks discussing the International Arctic Research Center data sets. To kind of bridge the second day to this third day, Charles Miller and Peter Griffith will be talking about the Above program, and both in general terms, but also specifically about the airborne remote sensing data sets that Above has collected within the Arctic Colors domain, study domain. Jim Churnside will be presenting some exciting results based on their oceanographic lidar in the coastal Arctic. And Atsushi Matsuoka is pulling double duty for us this week, providing a second presentation addressing Arctic satellite remote sensing challenges and gaps. This will be followed by Q&A for all speakers, and we'll have some breakout groups with a revised set of questions. So they'll be they're generally different than what we've discussed earlier in this week. But the aim is not necessarily to just focus on remote sensing, but remote sensing in the context of the other topics. We'll also come back for a discussion as a whole group, and then at the end of the day, we'll have a wrap up and adjourn the meeting. Okay, and so we are ready for the next person. Okay, so Hajo, if you are ready to proceed, please do so.
Yeah, thanks, Antonio. So I'm Hajo Eicken. I'm director of the International Arctic Research Center, or IARC, at the University of Alaska Fairbanks. We're located on the Trothiada campus on the traditional homelands of the Lower Tanana Dene. And we're a center that brings together international collaborators to generate information products and data that actually make a difference. So we have quite an applied perspective to some of the work, providing decision support. But I appreciate the opportunity to speak to this group when Maria Giorgio asked me to talk a bit about some of the data that are available through IARC. Of course, I want to be sure you understand that this is just a subset of numerous data sets that a range of people have collected. You've already spoken to this, Antonio. There's lots of other data out there, but I try to focus on three aspects of data that have been compiled and are curated at IARC that may be of broader interest to Arctic colors, that also bring up some of the issues that you may want to consider if you haven't already done so. And of course, you've already put in quite a bit of effort. I just want to make sure you can see the screen here with the presentation. I also want to acknowledge, I mean, the group that's been moving Arctic colors forward, just a tremendous service to the broader community. The timing is ideal for what you all are trying to achieve. And I would just like to focus on these 4 different aspects here, real brief. You'll have access to the presentation with some of the links to how to access some of these data sets. And I also want to reference Joel Rowland's presentation. I was in travel, so I wasn't able to join earlier, but you've already heard a bit about the Department of Energy Interface Project as well, which is a great link between some of the things that you're trying to achieve. Now, in terms of history, I do want to acknowledge the NSF Arctic Data Center out of UC Santa Barbara, who've been a tremendous partner in helping migrate the larger data holdings that were assembled at IARC over the years. As some of you may be aware, IARC was founded as a Japan US Collaboration International Center. So there's a number of long-term measurement and data collection activities that are still ongoing. But over the past year, we've migrated from an archiving perspective that data into the Arctic Data Center, and working with Matt Jones, Amber Budden, and their team has been great. They definitely are a tremendous resource also potentially for the Arctic Colors group. And of course, I realize that you're going to be relying on NASA DAX, but there's some aspects that I wanted to briefly cover as well in this presentation that may want you to also delve into the NSF ADC's holdings. And then I'll briefly talk about an Arctic data portal, climate data and broader data set portal that's linked into DOE initiatives. Talk a bit about, give you an example of 2 of those data sets that are curated under this umbrella. And then finally talk a bit about the Alaska Arctic Coastal Observatory Knowledge Hub as an example of data holdings and data that bridge the realm of biogeochemical sciences, biological oceanographies, and concerns and interests of coastal communities in the region. So the first aspect is something that you've already heard a bit about. Those of you who were here for Joel Rowland's presentation, is DOE's interface project that has already done quite a bit to assemble data relevant in the context, in particular, of the hierarchy of models that DOE national lab researchers use. The leads for the work that focuses on data management and creating a curated data set are Scott Rupp and Bob Bolton at IARC here. And they've been tasked with creating a curated data set in a portal that supports model development, benchmarking, and validation. The focus, of course, being E3SM and the DOE suite of models. But there's a number of things that I feel are strongly relevant for this group as well. I should point out that this is still in the developmental stage, and some of what I'll be showing you really will only start to become available in 2022, but that may still be in time for some of the things that you've pointed out in terms of field phase synthesis. So the 2 elements of this initiative or activity that I just want to briefly highlight here are the Arctic Data Collaborative, or ARDAC, which is an initiative of University of Alaska Fairbanks that's led by Scott Rupp. Here the goal is to curate data sets that are of climate data record quality, but are of potential interest to a broader range of users, including agency and community, local government users, as well as the research community with a focus on Arctic Alaska, or all of Alaska. And that ties in with the Arctic Climate Data Node. That is a project that's currently in the very early stages that would create a climate data node at University of Alaska Fairbanks to tie into Department of Energy data center holdings. So this would house both CMIP6 model output as well as a range of other data sets that are particularly relevant from a model benchmarking perspective. And just to give you a feel for the type of work that's ongoing now, I just want give you an example of the type of work that this team is doing, that's led by Katrina Bennett with Los Alamos National Lab and Bob Bolton and IARC, is that they're essentially, so the study region you've already seen in Joel's presentation focused on Arctic Alaska at this point, and adjacent regions in some areas. So this group is going through all the relevant data sets from a terrestrial hydrology perspective right now. There's other teams that are part of Interface that are focusing more on biogeochemistry and coastal and coastal ocean processes. But this here serves as an example. So they're reviewing existing data holdings from a range of different agencies, USGS, State of Alaska, university researchers, and others. And what's shown here is sort of a summary of some of the data that they're reviewing in terms of quality, continuity, and availability. The idea being that all of this will then be integrated and made available through this portal. You see there's a lot of snow measurements out here. I do want to acknowledge, I saw Melinda Webster's on the meeting here as well. Of course, she knows a lot about snow remote sensing as well. So there's a lot of connections to other ongoing programs. And again, this is maybe more than you want to know, but they're delving more deeply into looking at actual individual variables such as USGS water quality data records that go back to the early 50s. And if you want to know more about this, here's another one on soil properties. Of course, all of these things may only be marginally relevant to Arctic colors, but of course, a lot of this is being done from the perspective of land-ocean interaction input into the coastal ocean. So the modeling team, Ethan Kuhn and others that are part of the Interface project are using various schemes for runoff simulations that have some biogeochemical process representation. The other data set that is part of this curated set is a landfast CS extent and seasonality climatology. This is work that's led by Andy Mahoney at the Geophysical Institute at the University of Fairbanks, has a number of other collaborators. This is work that's also currently underway and is supported through Bureau of Ocean Energy Management. The idea being that roughly 2 years from now, there will be a very detailed climatology and associated data sets for landfast ice data, mostly extent seasonality. There's some, as seen here by these yellow stars, some deployment of sensors as well, so that there's some through ice measurements, ice thickness in particular. But this may be of interest for the group as well. And again, all of this part of the RDAC data portal. The other data set I wanted to highlight in a bit more detail, because this may be of particular interest to this group, is work that ties in with the MOSAIC experiment. And I don't know how much you know about this, the more than 1 year drift of a polar stern-based expedition throughout the Arctic Ocean. Melinda Webster spent quite a bit of time there. I see Bonnie Light, who's part of MOSAIC, is on here as well. What I'm presenting now is part of Marc Augier's work as a PhD student and now postdoc at IARC. He was one of the people responsible for working with the CS Physics and CS Biogeochemistry team and biology team at MOSAIC to develop a best practices approach for ice coring, ice core data processing and analysis. And so that's essentially what I'm presenting here as a brief summary. What's important is that for MOSAIC, for a number of reasons, there's work that was carried out at a coastal site at Utqiagvik in northern Alaska, and that data may be of direct interest to this group. You'll see some links to how to access the data sets here. The CS property climatology builds on work that we've done at UAF for almost 2 decades now, with core physical variables here listed at the very top, including thickness, temperature, density, salinity, oxygen isotopes. But the most recent data set, the Coastal MOSAIC 2021 Spring Field Campaign, is of potential interest because that includes nutrient, trace metal, chlorophyll A, and other data of biogeochemical relevance that were collected in particular by Laura Whitmore with UAF. And so also from the perspective of benchmarking data and model validation, I just like to highlight these data. Here's an example of sort of the synthesis of this data set that you can also access at the NSF Arctic Data Center that has all these data holdings. This is part of a paper that Mark put together last year. So this provides a framework both in terms of looking at different stages of the ice growth season, represented here through freezing degree day stages, early in the season at the left, 300 to 600 freezing degree days, and then transitioning over into thawing season or thawing degree days. And shown here are just examples of the climatology, if you will, of sea ice salinity as one example, and temperature at the bottom. So this data is available now and is being built further out. One example of that further building out is the coastal mosaic work at Utqiagvik that was supported as part of a project that was meant to collect data at the mosaic camp. I don't know how much you know about this, but there were a number of challenges related to both COVID and other issues that presented a challenge for, in particular, for the biogeochemistry team. So there was a very small campaign that was part of an NSF supported project at Utqiagvik that collected a continuous series of data from the late winter ice growth season into the spring, summer ablation season transition and landfast ice. This is the example of the data here. Laura Whitmore has been responsible for a lot of the macro and micronutrient work and other biogeochemistry, and then Mark Ogier for the geophysics. So that's something that you may want to be aware of further as well. And I should point out that this work is also part of the Ocean Best Practice, or ties into the Ocean Best Practices initiative that's been promulgated by people like Jay Perlman and others with International Oceanographic Commission, such that the whole set of protocols and scripts, programs to manage and handle this data in a consistent fashion that was developed by the broader Mosaic team is also going to be available through the best practices portal. So the final point, just a final last couple of minutes I wanted to make is that something for you to consider, and it's great to see the Arctic Colors team sort of take the long view and start these discussions early, because while I understand that the focus is on biogeochemistry, linking satellite data, field observations and modeling, you will be working, or most of the people who are part of the fieldwork teams presumably will be working in Arctic coastal areas that have been the homelands of Inupiat and Yupik people for centuries to millennia. And so this is something that entails a responsibility, I would say personally, of course, being somebody based on indigenous homelands, to engage with these groups. And now is a good time to be thinking about that, whether you want to do any of this or to what extent. But as somebody who's worked collaboratively with indigenous knowledge holders, I see substantial value, both in terms of the expertise, their contributions, but also in terms of ensuring that the data and the model output is relevant in a broader societal context. So there's a number of initiatives underway currently that are tying into that. I can't cover any of them. I just wanted to highlight Donna Hauser's work here at IARC, who's the lead for the Alaska Arctic Observatory Knowledge Hub, or AOK. It's a community of, or a group of community-based observers in a number of Arctic coastal villages in Alaska who've been making observations of the coastal ice environment and ocean environment now for almost a decade and a half. More than 7,000 observations that are accessible through a publicly available database. If you visit the Arctic AOK websites, you'll see more of that. So they've been conducting a range of different observations that may be of interest, some of them for this group as well. Here are some observations from Qikiqtaguk or Kotzebue by Bobby and Vince Schaefer to Inupiat ice experts for the 2019 season. And of course, they're looking at the sea ice holistically from a food security access perspective. But you see a reference, for example, here to CDD measurements very warm water events that displaced crab from the area, a subsistence resource for the people in the region. And so I just want to make sure that you understand that these observers also have been deploying in addition to making observations from their perspective, have been deploying sub-ice CTDs. Here's a time series for 2019 that Hisatomo Waga helped compile. I think he's in the Zoom meeting here as well. Can probably talk more about it, but I just wanted to highlight that in addition to under ice salinity. So this is measurements directly underneath the landfast ice cover in Kotzebue Sound over the course of the spring-summer transition 2019. You see increase in water temperatures here after fast ice breakup. Notice that there's also through fluorescence sensors on the CTD some measure of algal biomass. There's this warm water episode that Bobby Schaefer referenced, with temperatures up in the 60s Fahrenheit, and then potentially evidence of a second bloom. So these types of observations in coastal waters that community-based indigenous observers can provide can be of tremendous value, and that's just something I wanted to highlight. So with that, again, I appreciate the opportunity to speak to this group. I'd be happy to answer questions later. Here's contact information, and this presentation will be shared with the broader group as well. Thanks.
Thank you for that presentation. Let's go ahead and move on to Charles Miller and Peter Griffith.
Great, thanks. It's wonderful to follow Hajo and hear all the work that UAF are doing, and they are critical contributors and partners to the above activities that I'll talk about right now. I've got Peter Griffith with me. He's the project manager for Above. I'm one of the science leads, and we're going to give you a quick overview of the Above field campaigns and some of the aircraft data that we've acquired that might be of interest and value to Arctic Colors. Next, please, Peter. So real quickly, Above is similar in scope to what Arctic Colors is envisioning. It's a decadal scale, NASA-led terrestrial ecology program, which is looking at environmental change in the Arctic with the overarching science question of how vulnerable or resilient are Arctic ecosystems to societal and environmental change. Next, please, Peter. Above has a relatively large domain. It's approximately 4 million square kilometers, and you'll notice that it's the land areas and the watersheds that are immediately adjacent to all of the Arctic Colors areas. So there's a lot of information that can be leveraged. There's the possibility to establish some pre-Arctic Colors baselines. And in this data synthesis spirit, there are definitely some Arctic Colors specific analyses that could be undertaken with the Above data that haven't currently been targeted by Above researchers. Next, please, Peter. Okay, why don't you take over and give the quick spiel about where the data are and how to access them.
Okay, so all of the Above data are being archived at a NASA archive center. The ORNL DAC is the primary biogeochemical archive. We also have quite a bit of UAV SAR data at the Alaska Satellite Facility, and the Elvis lidar data are at NSIDC. As data reach the mature stage of being archived, we're also putting them into what we're calling the Above Science Cloud, but it is running on ADAPT, the system that that Antonio mentioned in his talk, which is a system. ADAPT stands for the Advanced Data and Analytics Platform. It is at the Goddard Center for Climate Simulation, and it allows us to provision 1 to hundreds of Linux machines and 1 to dozens of Windows virtual machines that are built to specification for investigators with the code that they need and the the software that they need. And all of the data that above are taking are, proximate on spinning disk to these virtual machines. So it allows investigators, once the code is up and going, is to on one Linux VM, then you can spin it up to dozens to hundreds to speed the rate of process. Some of the data collections that are on ADAPT that are relevant to Arctic colors, I've put the blue arrows next to some of the ones that came to mind. One is the 80 terabytes of above data from the 3 archive centers that I mentioned. It also has many terabytes of ISAT-2 data, all of the Landsat for all time for this region is staged there. The MERA and MERA-2 reanalyses, I suspect, would be very useful. This says select MODIS data, but in fact, Goddard also has the MODIS Center, and any MODIS data from any time period are available to be provisioned to an investigator. And then finally, this NGA, this is not publicly accessible data. You have to have NASA IT credentials and agree to Digital Globe and National Geospatial Intelligence Agency copyright guidelines for use of that. But there's over 4 petabytes. And this includes thousands of coastal stereo image pairs for DEM generation. And I checked with Claire at Polar Geospatial Center. They're doing the Arctic DEM that I'm sure that you folks are aware of. The Arctic DEM is a DEM at a particular point in time. To her knowledge, no one has done the time series analysis dating from about 2010 to 2012 is when systematic stereo imagery of the Alaska coast began. So that's, I think, something that could be very useful.
Great, thank you, Peter. There are a couple of above summary papers that have been published, and in the backup you can find more information about other collections here at Environmental Research Letters, where there's an above focus collection. I'll point you especially to the Scott Getz paper that is an overview of above to date, and it also includes some critical knowledge gaps. And then for what I've been talking about, there's an overview paper of the Airborne campaign that we conducted in 2017, and then have continued in 2018-19, and hope to pick up after pandemic restrictions will allow us in the coming summer. Next, please, Peter. So for overall, the Airborne campaigns are allowing us to unify site level process studies with satellite data, and they're providing this critical intermediate spatial and temporal scales. And so we're really using this to link things together and provide the very difficult to do in the Arctic scaling analyses. Also, we're demonstrating some new remote sensing technologies and multi-sensor data syntheses. Next, please. Campaigns to date have been in 2017, 18, and 19. There were quite a few sensors deployed in 2017. This include the L-band SAR, Avarice, Elvis, AirSWAT, CFIS, which is solar-induced chlorophyll fluorescence, Arctic CAP, which is carbon dioxide, methane, and carbon monoxide in situ measurements in the atmosphere. SENS is methane and CO2 remote sensing LIDAR. We also had P-band SAR. Then in 2018 and 19, we repeated with L-band SAR and Avarice and got some wonderful coverage in 2019 of Elvis, delayed through 20 and 21, and then hope to go back in 22 with L-band SAR and Avarice, and then our colleagues from DLR will bring over a payload on the Halo aircraft. In 2023, we'll have a cold season campaign in conjunction with SnowX, and that will cover interior Alaska and the North Slope, particularly along the Dalton Highway. And that might be of interest to this group as well. Next, please, Peter. So if there are any requests, particularly for avarice data, please do send them to me. We will begin sorting all of our backlog from 2020 and 2021, in addition to any new requests in approximately January to put together the detailed flight planning. Next, please, Peter. All right, so I just want to go through now some visuals and give you an idea of some of the data that are available from the above airborne campaigns, and let you know that while we have not targeted the coastal zones specifically, particularly out into the water, we have had some serendipitous coverage of a lot of the river areas adjacent to the Arctic coastline. And I'll show you some examples there of the types of things that are available and could be made available or collected new specifically for Arctic colors. So let's start with L-band SAR. Next, please, Peter. This is just a highlight that there's a paper, if anyone's interested, that is a really detailed, what we call cheat sheet to understanding each one of the lines, the 60 or so lines that we have laid down as the backbone for the remote sensing in above. And these SAR flight lines have been the lines against which all of our other remote sensing measurements have been leveraged. Next, please, Peter. Okay, and so here's an example of all the different flight lines. We've broken them up into Alaska or A boxes and Canadian or C boxes. These are roughly the way that they get flown on an individual flight day. And they're also kind of thematically grouped together. Next, please, Peter. Here's an example of an inland delta. So this is the Slave River flowing into the Great Slave Lake. And you can see the type of information that's available. The individual pixel resolution is approximately 5 meters from the altitudes at which we fly both the L-band and the P-band SARs. And you can see that there's some information on not only bathymetry, but how the flow is going out into the lake. Next, please. We've also done a lot of work in the Yukon Delta. Here is looking at some of the areas that have been affected by recent or even longer term fires. And so you can clearly see the fire scar here for the Big Mouth Lake fire and the difference in the polarized SAR between the fire scar area and the greener, unburned, undisturbed areas outside the fire scar. Next, please, Peter. We're also able to take that information and turn it into quantitative data. And so you'll see that within the fire scars, the active layer thickness based on subsidence is actually significantly deeper within the fire scars as compared to the external to the fire scar undisturbed areas. And the soil moisture is enhanced. And these are both really compatible with the degradation of the permafrost underneath the areas that have burned compared to the undisturbed areas. Again, these will be available for people to look at in more detail. I just want to give you a quick summary now. Let's move on, please. So we have approximately 450 areas where we've acquired avarice data. In some cases, we've acquired contiguous maps. In other cases, it's transects or surveys of particular sites that people are interested in. Here's the map here, and now we'll go through some examples that'll be, I think, of keen interest to Arctic colors. Next, please. This is near Cambridge Bay at the CHARS facility, and this shows you that not only can we image the inland waters, but we can use the information from avarice to obtain and retrieve information on the vegetation. So there was some discussion on day one, particularly about lignin content in the runoff. And here you can see we can map out the actual lignin content of the vegetated surface. And this could be done anywhere that we have the avarice data acquired over land. Next, please, Peter. Okay, again, the Big Mouth area down in the Yukon Delta as imaged now by avarice. And again, you can see the clear distinction between the burn scars and the undisturbed adjacent permafrost areas. Next, please. This should also be of keen interest for those who are studying runoff and fire runoff. Here is a portion of our NOAA raster. And so this was purposely stopped kind of at the edge of the coastline there, but would be easy to extend into the sound. At the lower right-hand corner, you can actually see a bit of the Baldwin Peninsula, and COTS would be just a little bit to the south of this collection of images. Next, Peter, we're going to kind of work around the perimeter of the Arctic colors, and the next one should be Barrow. Yes, so here's the Barrow area. This is because of all the infrastructure and research that's been done in Barrow over time and continues to be done there. This is a keen area, and so we visit it whenever possible. It's really hard to get a good flight day at Barrow. You can see on this day, the 14th of July, 2017, even though it was nominally a clear sky day, on the lower right-hand portion, you can see that while we were making these acquisitions, we did run into some popcorn clouds that weren't in the forecast, and we have to deal with that. But the next slide will show you what it looks like in 2019. And so we've gone back several times to make this same set of acquisitions. We get different colors in the water, as you can see, and different periods of vegetation growth. Next, please. We've also looked at a portion of the Colville Delta. And so here's what those lines look for. We were actually making measurements of Neaxtut and some of the sites that people had down there for vegetation, but continued the lines out to capture this part of the Delta, and could obviously go further out into the coastal oceans if that were desired. Next, please, Peter. Here's a raster of the Dead Horse area. This was actually being done for viewing the oil and gas exploration, but this raster goes all the way from the Kaparik River on the left to the Sag Delta on the right. And again, if there were interest, could be extended out more into the adjacent coastal areas. Next, please, Peter. Above, researchers are also keenly interested on Herschel Island and some of the coastal degradation that's taking place there. I bring this up particularly because Ilse Meyer-Smith and her group are there usually for the entire month of July and into August, making UAS measurements and taking samples on the island. And so there would be opportunities to coordinate with them and perhaps request some UAS, very, very high resolution data along the coastline of Herschel Island. Next, please, Peter. Which should be the Mackenzie Delta raster. Yes, so here's what the raster in 2017 looked like, and I show here just the negative, which is the hydrology mask. So the water mask that's been done and taken from this approximately 100 by 100 kilometers squared raster. It's 35 or so lines of Avarice all stitched together. Next, please, Peter. And just to show you what this looks like in more stark relief, this is done at 5 meter by 5 meter pixel resolution. It's over 400 million individual pixels, and it allows us to analyze the optical qualities of the water. We also have the main channel, which I think is going to show up in the next slide, and plans to extend out not only to the coastal zone, but well out into the Beaufort Sea. So if you could switch to the next slide. Here's the 2019 raster, which, as you can see, is incomplete due to cloud cover and some other operational things, but we've got more of the coastal ocean and both the main channel in the east and going out into the east channel, the main channel in the west and going all the way out into the eastern channel. Next, please, Peter. And I just wanted to give a teaser on an IDS project that we have that's using Echo Darwin. And we've developed not only the full Arctic Ocean, but we've got high resolution, so 1 kilometer simulations for the Mackenzie Delta area. And so here's what the plume looks like in terms of sea surface salinity on the left-hand side or sea surface temperature on the right. And we're running this with specialized Mackenzie River runoff models. And also we have fully coupled data assimilation for the ice at the same time. And so we can look at and simulate all of these during the ice retreat, and during the ice advance in the fall, and look at the full seasonal simulation. I believe that that is the last chart to speak to. Oh, sorry, one more chart. So looking at what Atsushi spoke about with the recent Amundsen cruise and some of the Mannino points. So here are the points that we'll be flying transects over during 2022 out into the Beaufort Sea and adjacent coastal areas. And then I think that was the last one. Yes, so any questions, here's contact information and the website for above, where you can find out about all of the airborne activity and data sets that have been acquired. Thanks very much, and look forward to answering questions.
Thank you, Charles and Peter. We're holding questions until all the speakers have presented. Just be prepared if you'd like to, for those who will have questions, to speak up when that session begins. You can also type them in the chat as well. Okay, so next up, we have Jim Churnside talk about airborne lidar of the coastal ocean.
My browser doesn't want to let me share my screen.
Okay. Would you like to try to exit and rejoin? That seems to work.
Yeah, I think so.
I don't know if Zoom has changed this, but when entering Zoom from a browser, it didn't used to let you share a screen. You had to have the application running on your computer. I don't know if that's changed now, though.
Yeah, I've had the same experience, but Jim was able to share when we gathered before the session started at 1, and that seemed to work just fine. So he is able to share it, just not at the moment. Jim, if you're still on and you're having difficulty, if you would like to send the slides either to Maria or myself or Heather. Actually, myself or Maria probably would be better. So Heather's kind of managing some other aspects of this meeting. We'd be happy to flip through them for you. And otherwise, we might move on to Atsushi and then come back to you after Atsushi speaks, if that's all right.
Yeah, Antonio, let's do that.
Okay, I see that Jim is logged in, but I don't hear him. So Atsushi, would you mind proceeding,
Sure.
please?
Yep.
Thank you.
All right. Can you see my screen?
Yes.
Okay, so I'm going to talk about the Arctic remote sensing, especially ocean color challenges and gaps. When you look at the polar seas from space, you might see land, ice, water, or clouds. Removing a cloud, the sea ice looks like white, but water looks black. Clearly, the sea ice influences light signature measured at the top of the atmosphere by ocean color sensors. The question is how this influences water reflectance retrievals in the black target. This is what I'm going to talk about. So the ocean color are very useful as listed here, but it's important to note that there are some obstacles for use of the ocean color data in polar seas. Indeed, we addressed these issues in the IOCCD report 2015. There are 4 main obstacles: frequent cloud cover, high solar zenith angles, unique optical properties, and possible pixel contamination due to sea ice. For the first point, the frequent cloud cover can be partly compensated by many ocean color data nowadays available, and also thanks to the many revisit due to the polar orbiting. So this issue can be partly solved. The second issue, high solar zenith angles, is being examined by the ongoing NASA ROSES project led by the Knut Stamnes and co-workers. So I won't talk about that in my presentation. The third topic, unique optical properties, are partly documented by previous studies. But as I mentioned on Monday, optical properties resulting from the permafrost thaw or coastal erosion might be very important. So these optical properties need to be examined in the coming years. In my presentation, I'm going to focus on this pixel contamination issue due to the sea ice. The question is, does this matter for examining biogeochemical processes in changing Arctic coast? So my short answer is yes. So I'm showing you the example of the composite image using Landsat 8 during the June when spring freshet occurred in the Mackenzie Delta, overlay with sampling stations taken during the Nunavut field campaign 2019. Clearly, sea ice influences the ocean color data, particularly for spring freshet. So if we want to address the dynamics of organic matters, particularly for this time period, sea ice does matter. So ocean color sensor at the top of the atmosphere receive radiance from various sources. We are interested in retrieving the water reflectance as accurate as possible, but it is important to note that there are many sources of contamination, including snow and ice. So the objective of my presentation today is to evaluate the performance of commonly used atmospheric correction algorithm, particularly NASA standard and ESA standard polymers in terms of adjacency effect and subpixel contamination. The tools that I'm going to use include 3D radiative transfer Monte Carlo simulations, as well as ocean color data. This schematic diagram represents the Monte Carlo simulations. So here is a virtual sun. So I launch a number of photons from this virtual sun. Some of the photons can actually penetrate into the water column, reflected back to the atmosphere toward the satellite sensors. So what I'm going to do here is that first simulate the top of the atmosphere reflectance, and then apply the atmospheric correction algorithm to the top of the atmosphere reflectance to retrieve the water reflectance. So in this case, I would distribute sea ice on top of the ocean. So lower panel represent the geometry of my simulation setting. Is a virtual sun and sensors. This is the top view of this setting. So for example, delta phi is a specular reflection direction, where when we put the sensor in this direction, this is delta phi, 90 degrees. So when you put the sensor, this measures backward, which is delta phi 180 degrees. So now I'm showing you the top of the atmosphere reflectance, as well as water reflectance just above the sea surface, which is shown in this blue line. So black line represent the TOA reflectance over the ocean without sea ice. Gray line represent the over the ocean having the sea ice in the middle of the ocean, as shown in this figure. It looks like a thick gray line, but actually is a number of the lines overlap. A red line represents the top of the atmosphere reflectance over the ocean having a sea ice concentration of 10%, as shown in this figures. So when you increase the sea ice concentration to 50% or 90%, this is what we get. So clearly, sea ice influences the top of the atmosphere reflectance as expected. So now I'm showing you the top of the atmosphere along this transect. So this is a result. So as expected, when you approach to the sea ice, so we can clearly see this adjacency effect near the sea ice. So important message from this figure or this result is that sea ice contamination can be observed within 20 kilometers from the sea ice edge, which is consistent with previous study presented by Belanger et al. 2007 using the 1D radiative transfer simulation results. Now we apply the two atmospheric correction algorithm to the top of the atmosphere reflectance. So these are results for that. The black line represents retrieval of water reflectance using NASA standard atmospheric correction, where the red lines represent result using ESA standard polymer at the two different geometries. So results show that the using NASA standard algorithm provided the overestimate compared to the true spectrum at the two different geometries. In contrast, polymer does a better job for retrieving water reflectance for this simulation case. Now I do the similar thing, but for the ocean having a different concentration of sea ice, 10%, 50%, or 90%, to see how this impact on the retrieval of water reflectance. Similar story here. So when you apply the NASA standard, we can clearly see the overestimate, whether when you apply the polymers, it does a better job. So far, I have shown the result using the radiative transfer simulation. Now I'm going to show you the ocean color data to see if makes sense or not. So I chose this particular image to examine this adjacency effect. So when you apply the NASA standard atmospheric correction, you clearly see the adjacency effect along the sea ice edge, as shown here. In contrast, as shown by the simulation as well, so a polymer provided the better result, and no adjustance effect was found in this case. So this is a different view along this transect. So I extracted the values along this white transect. And as expected, when you approach to the sea ice, the reflectance is going to be higher toward sea ice edge when you use the NASA standard, which is consistent with the simulation as well. So this is the last slide, I believe. So I wanted to examine this subpixel contamination issue for the top of the atmosphere. So what we did here is that using the Landsat image, which has a spatial resolution of 30 meters, we sampled into the 1 kilometers as a mimic of the medium resolution ocean color, such as Morris, to see how this resampling affect the top of the atmosphere reflectance. So we choose the 3 different sites. The area where the water is highly influenced by sea ice, medium influence, and low influence waters, to see how this sea ice impact on the top of the atmosphere. So this is the result. So black line represent the original spatial resolution, so 30 meter resolution. These data are used as a reference. So red line represent the resampled data into 1 kilometers. So you clearly see this subpixel contamination issue. So when you use this data, 1 kilometer spatial resolution for sea ice distributed area, we need to be very careful for interpreting data in this area. So this is a summary. So basically, I'm saying that the polymer works better, especially for this icy waters, for both distance effect and also subpixel contamination. But there are some challenges, of course. So as I said, polymer does a better job for this to effect, and it is computationally expensive. So we need to think about how we can apply for the upcoming hyperspec data, for example, for the PACE, GRIMR, and SVG. And higher spatial resolution, of course, is desired to examine the dynamics of the coastal processes. And also this is important to reduce the subpixel contamination issue. So last topic, Antonio briefly mentioned that, but for the obvious reason, under-ice bloom cannot be seen by ocean color data. However, when we describe the optical properties of snow and ice, then we might be able to somehow estimate light below the sea ice. So this might be useful for estimating under-ice bloom with assumption about the nutrient below the sea ice. This is, of course, challenging, but might be possible in the near future. All right, that's all. Thank you.
Thank you, Atsushi. I'm going to go ahead and proceed with sharing Jim Churnside slide.
You want me to try it once first?
Sure, go ahead.
I think we got it.
Yes, wonderful.
Excellent.
It's magic. Sorry for the Okay, now it won't. There we go. Sorry for
Looks
the
good.
difficulties there. So this is a photo of the NOAA lidar in the NOAA Twin Otter. The optics package is back in the back. The half rack with the electronics is here, and I'm sitting up front watching the data come in. I want to talk a little bit about the characteristics of the lidar for people who might not be familiar with them. It uses a 532 nanometer laser. This is a very robust source. And we've flown these since the late 90s. This wavelength gives you the best penetration in coastal waters. In oligotrophic waters, a bluer laser would work better, but there's not a easy to get one available. So we stick with 532. We have a 5 meter spot size. This is small enough that it can penetrate between ice flows so that we can get an idea of what's going on under the ice with ice concentrations of 90%. We have a 2.5 meter spot spacing on the surface. This gives us high spatial resolution along the flight track. It also means we can do Fourier transforms along the flight track without worrying about aliasing, and I'll talk more about that later. Our depth resolution is 15 centimeters to 1.3 meters, depending on what the target is. A hard target, the surface, the bottom, a fish, a whale, returns the pulse shape that was sent out. And so we can do a deconvolution or just look at the peak and get good depth resolution. If we have a distributed target like a plankton swarm, then it smears it out and we get about 1.3 meter depth resolution within that swarm. Depth penetration of 30 to 50 meters, depending on water clarity. In most of the waters in the Arctic where we've been working, it was closer to 30 meters. I don't think we ever saw anything 50 meters, and actually even less right near the shore. We use a dual polarization receiver. The cross-polarized return gives us a high contrast between the water return and phytoplankton in the water. This LiDAR has a high information content. Like ocean color, you can get a lot of different products out of it. Ice, subsurface plankton layers, mixed layer depth, internal waves, chlorophyll profiles, primary productivity profiles, information about the type of scatterer and turbulence in the water. We went and flew out of Utqiagvik the last half of July in 2014 and 2017, and the last half of May in 2019. These are the flight tracks, and there's information about the ice cover. The difference, like for July 2014, the difference between the fuzzy blue and the blue with the bigger marks on it is one is the ice edge when we first got there, and the other is the ice edge when we left. This is from satellite data. The different cross hatchings in July 2017 do the same thing. The first thing that pops out on these flight tracks is that they're not regularly spaced transects out from the shore as one might expect. Clouds, low clouds and fog are an issue. We were also interested in the marginal ice zone where we had broken ice. So we looked first for regions where we could fly, well, clear skies ideally, but regions where we could fly under the clouds and look into the water and then once we had those regions, we're looking for regions of broken ice. The most obvious feature in the lidar, because it does profiling, is subsurface plankton layers. On the right, we have chlorophyll concentration along a transect going into the ice pack. So at the beginning on the left, there's a plankton bloom right at the surface, and that drops down to a subsurface plankton layer. The white vertical lines are places where I've blanked out the return because of ice. Ice is absolutely easy to detect in the signal. It saturates the bejesus out of our receiver. And so we can see ice even through very thick fog. We can see down into the water through thin fog, but ice we almost always see when it's at the surface. And the bottom is the ice fraction inferred from the lidar in 1 kilometer segments. And it goes from 40%, from 0, obviously, up to kind of 40% in that first, and then goes down again. And I don't know if you can see it behind the other window, but it goes up to 50%, then again toward the right. One on the left was in open water. It's just a swarm. It's about 4 kilometers long, with a double layer on the left and then going to a single strong layer. I just included that because I think it's a cool looking image. We also see internal waves. This is an example from open water in the Chukchi Sea. There's a plankton layer at a depth of about 10 meters. And then there's 7 cycles of an internal wave on that layer. The plankton is displaced up and down with the wave as it passes through. This particular one had a 2-meter amplitude. We note also that those plankton layers we've seen in almost anywhere we've looked, they tend to be associated with the mixed layer depth, sometimes a little above or a little below, but generally pretty close to the mixed layer depth. So we can get an estimate of mixed layer depth. So those layers in July in 2017, 40% of the area in open water. In 2014, 50% of the open water flight tracks were covered with contained subsurface chlorophyll layers. There's an exponential decrease with ice fraction as we go into thicker and thicker in ice. In May, stratification really didn't exist yet, and we saw virtually no layers. Average strength of the layers in open water was 11 to 27 times the background scattering level. It's just a convenient way to measure the strength of a subsurface plankton layer. We can also, of course, apply our calibration coefficient and get the absolute chlorophyll concentrations. Strength was less under ice. The depth was, these layers were deeper in open water than they were under ice. Thickness of the layers was pretty close to 3 meters. In open water, under ice, didn't seem to make a difference. Here's a plot of layer strengths. This is from 2014. Again, it's a ratio of the concentration in the layer to the concentration in the background. In open water, there's 2 orders of magnitude plus variation in the strength of the layers. In the pack ice, there's less of a variation. The layers tend to be less strong again, and with less variability. We did some primary productivity modeling using Barenfeld and Falkowski's vertical generalized production model, used Modtran surface irradiance spectra with no clouds for 71 degrees north at the time we were there, a water temperature of 0 degrees, no ice, a background chlorophyll concentration of 1 milligram per cubic meter, and a 3-meter thick layer with 10 milligrams per cubic meter. And then we moved this layer from the surface down deeper. As we went from the surface down, the primary productivity increased to a peak with these conditions at 10 meters and then decreased. So that's a peak in the primary productivity when the layer is about where we were seeing layers. These are a couple, well, one example, this is one profile from about 2 million. We didn't plot up all of those, obviously. We got, so the chlorophyll had a maximum at the surface, and then another subsurface chlorophyll layer at, again, about 10 meters. We got photosynthetic available radiation from an uplooking
Uh-oh, Jim, are you there?
Yeah, I think. Jim?
I think he's frozen.
All right.
And if you can hear, you might try turning off your video. That'll use less bandwidth.
Well, he's gone. Let's wait a few minutes to see if he comes back. And then perhaps we can tell him to turn his video off, as Mai suggests.
Yes. In the meantime, maybe if there's a question for any of the other speakers, so that we kind of try to be more efficient with the time that we have available. Any questions for any of the speakers?
There's some popping
Aside
up
from
in the
Jim,
chat.
Okay. Let's see. Okay, so Emmanuel Boss asks, what about ISAT 2 utility for the Arctic Colors area? We have ocean color folks on the ISAT team now, such as Kelsey Bisson. Be great to know how well it works there. Have any of the speakers, Atsushi or Chip or Peter, has anyone used ISAT 2 to your knowledge in the coastal Arctic?
So regarding the ISAT-2, during the United campaign, we had considered to use this to examine the sea ice thickness, especially because this was one of the issues when we went out during the early spring, let's say April 2019. So in terms of security purpose, we wanted to know the sea ice thickness, but at that time, unfortunately, ISAT-2 was not available, but for the Arctic Colors campaign, it would be very useful to use this, especially if the early spring period.
Kelsey Bisson noted in the chat that she's used ISAT-2 in the Antarctic, and the depth resolution thickness precision is incredible. She's just starting to work with it in the Arctic. There were some other comments. Charles Miller commented that Jim Churnside July 2017 ISAT LiDAR data overlaps with the above July 2017 AVRIS data. So that would be some nice synergy between the hyperspectral AVRIS data and the LiDAR information, which provides the depth resolution. let's see. There's a question about whether the LiDAR that Jim was presenting was eye safe, and Joseph Shaw responded that generally, yes. We can ask Jim when he comes back on, hopefully. Jame Lu who's on the call, has been using ISAT-2 as well for a variety of applications. And Peter Griffith mentioned, yes, that ISAT-2 has been used for ocean retrievals. Presumably this would be like backscatter profiles, but also for bathymetry. Any other questions?
I just tried to call Jim Churnside to see what he was doing, and he turned on his phone and I could hear him giving his talk. I think he's still presenting. So I'm texting him to tell him that we're not hearing him.
Okay.
Antonio, can I share the screen for a moment?
Certainly.
If I can do that. Yeah, this is Chip Miller. Let me see if I can get the PowerPoint. Good. So share that. And you all should be able to see now the Elvis flight lines. And here you can see some of the long flight lines from Elvis. These are actually the ISAT-2 underflights. And so this is possible to coordinate the airborne lidar and the space-based lidar, and I'm sure we could do this with the NOAA instrument as well. This was Elvis on the G5, and so it was possible to go, 1,000 kilometers at a shot. Probably not possible to do that with the Twin Otter, but these are the types of things that we can think about doing in and around the coastal area. So you can see here at Barrow, in the Colville Delta, and near Dead Horse, there was a lot of acquisition that goes out over the coastal area.
Yeah, I'd be curious to know the differences between Elvis and the oceanographic lidar that Jim brought.
Elvis doesn't penetrate water.
Okay, I was wondering about it.
So they actually calibrate their surface by by flying over water. But
it's
interesting
useful for other applications.
Yeah. One interesting thing about those underflights for Elvis of ISAT-2 is that they're done for ahead of when the satellite is going to get close to that location, and they do point the satellite to pick up the Elvis. So we have to follow up and see how successful they did with some of those, because there were times when it wasn't clear exactly where ISAT was going to be overflying, but they thought that they'd be able to to pick up those lines.
Thanks, Peter. So there's another question. Frank Whitmer asked about what algorithm was used to generate the water mass from the Avarice data. I think that would be to Chip.
Yeah, thanks for that question. We have several algorithms that are used based on looking at different wavelengths and their very, very low reflectivity for water compared to what you see over a vegetated land surface. And so some of the typical wavelengths that are used are near 1600 or 2200 nanometers. And we've got, and the community have developed numerous types of simple algorithms to do that masking. So I think the one I showed there was mostly based on the 2200 nanometer masking.
Thank you. Rick Reynolds has a question for Atsushi. Ice edge plumes, either from melting ice or plankton layers, are common. Can you distinguish them from adjacency artifacts?
So my short answer is yes, using the high spatial resolution ocean Goddard, such as Sentinel-2 or Landsat 8. However, using the intermediate spatial resolution like Morris and Beard and so on might be very challenging. But using the higher resolution, yes.
I'm back.
Jim's back. Jim, we can give you a few minutes to finish off your slides. We really want to try to break at 2:35 for the breakout if possible. Would you like to go ahead and finish? We caught through slide 9. I think you just have just 3 more to go. Would you like to do that?
Okay. Let me so can you just can you easily put up my my last slide?
Yes,
I'm afraid, because it won't let me show.
Yeah, I understand.
So slide 9, so you got that. So it was the turbulence details that kind of got missed. We looked at turbulence in Barrow Canyon and found significant correlations between the turbulence in Barrow Canyon and upwelling conditions. Upwelling, more turbulence, downwelling, less turbulence. The main point I want to make is that there's a lot of information to be had in the lidar signal, ice, subsurface plankton layers, mixed layer depth, internal waves, chlorophyll profiles, and primary productivity profiles. These are both based on some model, biogeochemical or primary productivity model. I've used global models so far. These really need to be tuned for the Arctic. There are differences in chlorophyll packaging, for example. Type of scatterer from a cluster analysis, and turbulence. We also get information from ocean color sensors, and these are multispectral, not hyperspectral, and sea surface temperature on the aircraft. The main difficulty in flying in the Arctic, low clouds and fog. We were able to be very flexible in where we flew on any given day, and we're able to fly below a lot of the clouds we see, and the lidar will penetrate through fog unless it's extremely thick. So we managed to get data pretty much every day. It just wasn't necessarily at a particular location. And so I will quit there, and we can go into the question and answers.
Okay. We have time for a minute or two for any more questions. There's one specifically related to regarding the lidar. Someone asked whether it was eye-safe for ship operations, if someone was doing some field measurement work. Yes, our 5 meter spot on the surface is eye-safe at the surface, which means also we've also looked at relative eye safety for marine mammals. It's also eye safe for marine mammals at the surface, including walrus, which is a sensitive topic up there.
I'm sorry if I missed it, but what altitude does the aircraft fly at?
We usually fly 300 meters.
So you do have to be concerned about disrupting subsistence hunting.
Yes, walrus. Yes, we do. We steer clear.